Alright, so I apologize. As I said before, I just patched up those slides just before class, so I knew they look bad, and sorry about that. So in fact, I just added a additional slide, which is actually complementing the explanation I gave before, which was lacking this particular aspect. So kernels, we didn't talk about kernels. Again, I apologize. So let's see what are these guys. In this case, we are going to be using one-dimensional data, okay? Everything is going to be just fine as we use two-dimensional data, which are kind of images. Images are kind of 2.5 because they have also some thickness, right? But you can think about images as two-dimensional data, not spatial data. So here we think about 1D data. And we said we go from one layer to the other layer by using these kernels, which apply first here, then the same kernel, so the kernel is the collection of these three weights. I apply this guy to the second chunk here, and to the third chunk, okay? So this is the same guy, which is applied to different locations because we, again, exploit the fact that we are using data which is stationary, okay? The same feature can appear in different locations of the data, which is spatial location, is temporal location, we don't care, but it's in different regions of your data. All right, so.
Question before we go on. Is this usually normal that you have less neurons in your layer, or is this for illustration only?
Okay, that is also correct. Yes, I apologize. Right, so whenever you apply convolution, you're going to be lacking a neuron here, because otherwise, where would you send this connection to, right? So I would have this connection, and I don't have anything here. So there is another technique, which is called zero padding, which you're going to be adding as many zeros here and here, so that you're going to have the same number of neurons every layer. This is what we are doing, basically, most of the time. So
or
you
can do cyclic, and then you will remove the problem.
Yes, but it doesn't.
That's why there's not a full argument, right?
It doesn't work if you have images. You don't. If you end up one side of the image, you cannot see the other one coming in, right? So it doesn't really work for images, for example. Most of the time, we just do zero padding, which means I add as many zeros as here and here and here as the number of kernels divided by 2 floor. So here we have 3. Divided by 2, 1.5, floor 1. So I add one more 0 here, one more 0 here, so that I have 5 neurons here, I have 5 neurons here, okay? So in theory, usually convolution won't change the dimensionality. If they do, it's because I didn't pad my input, okay? You can pad, you can decide not to pad.
I don't quite get it. You can add it and just send it to 3. This is on your picture that's in the middle of 3, but you can connect the next one with the 3 of this, you just will have more neurons. Or you mean since it's the same kernel, it will be a duplicate? Oh, okay. Okay, I think I know the answer.
Okay, I didn't understand what you said, but I'm happy you understood what you said. All right, so again, here we have that we go from this layer to this layer by using this kernel, which is the collection of these 3 colors, over and over and over again, okay? So this one here is my first kernel associated to this layer. Of course, we can have multiple kernels per layer, but I didn't mention that. So here we have my second blue kernel, the blue, purple, and pink. And so this one, given that we have 2 kernels associated to this specific layer, is gonna make these guys here not scalar anymore, but they are R2 guys, right? The first element is associated to the convolution with this first kernel. So I have these 3 guys multiplied by these 3 and sum, I have first value. I have these 3 guys multiplied by 3 guys, sum together, I have the second value. These 3 guys multiplied by these 3, sum together, third value. This is the first item in the R here. Second item is going to be containing the scalar product, the projection, on this kernel with the input. Okay? So we are going to have here, this number here represents the thickness of this layer. So these balls are somehow coming out from the screen. Yeah?
So these different kernels, are they taking the same inputs from the previous layer? So is it that the inputs are the same and the weights are different, or is it the inputs are different?
The first one. Okay. So since you see there are different colors,
yeah,
they are different numbers. But here you have all these guys are the same guy. the same input, right? So you have your signal here distributed across 5 samples. And here you multiply this guy with the first kernel. So you have like a projection, right? So whenever you do a projection, you see how much of this kind of feature is located in here. And this is the first answer. So this one tells you what is the projection of this first location of your input with this kernel. So you have a kernel, and you have your input. You do the projection of your input on that kernel. You have the first output here. Then you do the nonlinearity, so you can go on. Instead, this guy here is going to be another kernel space on which you project, again, your input data. So here we have 2 kernels. Therefore, these guys are not scalars, but they are vectors, right, of size 2. And here we are using 3 connections, and therefore I have 3 values within my kernel. So we have number 3 here, because they are the connection. We have 2, because there are 2 different kernels, okay? Yes? No? Yeah, question?
Can we have a different kernel with like different features? So like 4 values in one kernel and 3?
Different sizes.
Yeah.
Yes, you can, but then you're going to be changing your network. So you're going to have your network, which is branching out. It's going to have like 4 branches, for example, and each branch has its own size. But each convolutional layer has the same number of items in a kernel. In every kernel, you have the same number of guys, because it's going to be just a tensor. I'm going to show you soon. But again, if you'd like to have different receptive fields, then you have different branches in your network. You can easily do that in PyTorch. You simply send your same input to different convolutional kernels, and at the end, you may concatenate everything, okay? Yes?
How do you avoid ending up with kernels that are essentially, have very, very similar weights that are really the same thing?
Good question. So as long as you initialize these guys with random numbers, and it's very likely these 2 guys are randomly, there are 2 different numbers. So whenever you have your weight space, your weight space, those guys are different points, and those guys are going to be stepping towards wherever the loss is going to go to the 0, right? So you have this guy here, given that I start here, and the other guy starts here. Both of them are trying to step in order to minimize the function, but they are still far away. It's very unlikely that they're going to be hitting each other, matching, because this stuff has a lot of up and down. So one will stop here, the other one will stop at a different location. But they may end up being...
Can it also happen that there's some certain number of local minima in your weight space? What if you start with more kernels than there are local minima in your
Then
weight
definitely
space?
you're going to have some kernels colliding to the same solution. All right, so yeah, that was supposed to be very short. Okay, right. 3 connection, 2 kernels. One more thing, 5 input, right? Who said those are scalars? This can be also the output of another convolution, and they may be 5-dimensional. So if we are, let's say, in a RGB image, this is going to be number 3. So every pixel has a R and G and B component. So this number is going to be 3. If these are whatever, they're going to have different features. So in each location, the descriptor at that specific location has a specific dimensionality. So as you can understand now, these guys here are also 5-dimensional, given that we had to project this guy on here, right? So we have these 3 guys, which are 15 elements now. They are going to be scalar product with this guy here, which is also 3 in this direction and 5 in this direction, right? So finally, you can collect all your kernels in some tensor, which is of dimension 3. So we have 2 kernels, 1 and 1, 2, of 5 elements, 1, 2, 3, 4, and 5, times 3 neurons. So first row, second row, and third row. So anytime you deal with 1-dimensional data, you are going to be ending up with collection of kernels, which are 3-dimensional tensors. Number of kernels, number of input features, 5, and number 3 of output, sorry, this special, this connection, number of connections. So, for example, before we were saying we are going from one image, one layer input image, grayscale, to six layers, right? So we were having kernels that were 5 by 5 because we are dealing with images, and they have dimension of 1, right? In this case, because my input has just one layer, so it's 1 times 5 times 5. How many of these we have? We said 6, right? So in 2 dimensions, like when we play with images, this guy here is going to be 6 times 1 times 5 times 5. That was the first convolutional module. Second guy here, we have kernels that now gets an input which has 6 dimensions. So this guy has to be 6 by 5 by 5. How many do we have? Also we have 6. So this guy here is going to be 6 times 6 times 5 times 5. So one-dimensional data, three-dimensional kernel, collection of kernels. Two-dimensional data, four-dimensional kernels. Three-dimensional data, yay, you understood, right? So pay attention. One-dimensional data uses 3D kernels and so on. Yes, please.
The kernel is actually like each line is supposed to be the weight, right?
Well,
What about the biases?
So these are, the bias is going to be just R2 times 3 here, right? So I have each of these will have a bias term.
So the bias term goes to the, node, not to the...
Yeah, the bias is like the offset, right? So basically, let me think. I think there are just, just 2. Because
just 2 for each
just 2, right?
Yeah,
so
yeah.
one bias for the first layer and one bias for the other one, right? Other quick, yes?
Wait, so if you have another set of parentheses with 3 different colored stars, then it would be 3 by 5 by 3?
So it's going to be, 3 by 5 by 3.
Okay.
If you have 7 kernels, you're going to have 7 kernels, 5, because it's where you start, and you end up in, you have a size of 3, right?
Okay. I was just thinking the fact that she raised that there can be various minimas in that weight space, and since you initialize them randomly, each of them are expected to converge to one of those minima, right, with the gradient. But I was just thinking if we can, in this dynamics of training like evolution, if we add some things like each weight point, which represents each kernel, I guess, repel each other, kind of in that weight, in that dynamics as well. I think that would ensure ensure that even if there are like less number of or same number of, I mean, it will ensure that 2 kernels don't converge to a similar.
Right. So if you add additional terms to the loss, then the network will try to perform well for whatever you ask. But usually what I like is to perform good on that specific loss I define. So if you add additional terms, I will do worse in the other task because I have additional terms I have to deal with. But you can try to have additional terms and see how you can introduce complexity in this kind of optimization problem. Okay? So that was just to show you that every layer here has a collection of kernels which are limited for the amount of connections, and they have definitely not scalar. They don't have to be scalar values. Okay, that was just for completeness. We're gonna go back to the notebook example where we have trained the convolutional net, we have trained the fully connected network. Both of them have the same number of parameters, but we have seen that the convolutional network performs much better than the fully connected layer. Because we are, again, exploiting those 3 specific property of the data, which were, no one is listening.
Locality,
stationarity, and one more.
Compositionality.
There you go. So given that there are these 3 specific characteristics, we can exploit them in order to improve performance, as we have seen. What does it happen if we don't have those 3 assumption working. I mean, if those 3 assumptions are not anymore valid, what does it happen? We're going to be seeing that soon. Are you ready? Are you excited? Should be. All right, so yeah, just as Alfredo said, we trained a fully connected neural network and the convolutional neural network with the same number of parameters. And we've seen that CNNs perform much better. And what happens if we made some assumptions when we constructed the convolutional neural net, which is the stationarity, locality, and the compositionality. What happens if we relax those assumptions? And we can test that by permuting our data. So the data that we used in the previous task looked like this. The first top rows, which basically the handwritten digits, those are actually grayscale images, but we plotted in color. And we just scramble it by flattening it to the 726 component factor, 784 component factor, and applying the random permutation, and then putting it back to the square image. It looks like this. So we don't see any numbers anymore. But can it tell? It's the same permutation. So can it tell what it was? And we simply going to train the convolutional neural net on the data with permuted pixels. And here's what we get. We do see the training, so the training loss is reducing. The training accuracy was good, but the generalization, the test loss was low, 80%. Sorry, the test accuracy was 80%. We will see. I would say it's quite high for the images as they looked. Let's see how the fully connected network performs. It's 89%. We don't remember how it was in the previous, so let's just plot it. All right. So we see that for convolutional neural network, for fully connected neural network, it's the first and the last beans. Nothing actually happened. And in fact, if you repeated the training multiple times and average it, you will see that it actually almost exactly the same. For the convolutional net, we see a significant performance penalty. The performance reduced by over 10%. So that's what happens when we basically remove the assumptions that made convolutional neural network work so well on images. All right. Questions?
It's a very general question. I'm not sure I understand. When you randomly scramble, this is. I'm not quite sure I understand what it means. What if I then write 4? Will it make out 4, or I have to scramble it and then in the same way?
So we know the label, right? So we know the image of 4 is 4. But when we see an image of 4, we see basically local patterns. The pixels nearby have the same intensity, right? And we see the edges, and basically back when Alfredo was talking about the cat picture, when we scramble it, we no longer have locality, right? The pixels nearby are different, but we still know that it's a 4.
That's right. But like next time, if somebody writes 4 and fits it, will it say it's 4, or first I have to scramble it in the same way
You have to apply the same. You have to apply the same scrambling transformation, right?
Same permutation with fixed random seeds. Yeah.
The whole point is to show that if those assumptions we had before of locality, stationarity, and decompositionality are not anymore valid because we scrambled the position, we cannot exploit anymore that specific characteristic of the input in order to improve performance. Whereas the fully connected layer doesn't have any assumption. So connection, you can scramble them; they are still the same connections, right?
You have to preserve the scrambling.
Oh yes, of course. That's a deterministic.
It's not 4 anymore, just label this.
Yes, it's a deterministic scrambling of the pixels.
I don't really know how to phrase this as a question, but it just like those don't look any different, right? Like
which one?
It does.
Well, like,
Pretty much.
yeah. So like even if like the label is still the same, like how it's surprising that it could easily with like 80% accuracy be like, oh yeah, that middle one, that's a 4. The one just to the right of it, that's a 1.
That's why convolutional neural network works so well. They can do magic even though we try to kill them, right? Because it's still you can still think the convolutional neural net. The convolutional neural net, you can still think about it as being, a fully connected layer for those central pixels, right? So although we have so many parameters that the network managed to learn something even without using the neighboring information. So right now, every kernel is just tuned to find these specific pixels in these specific locations. So that's why it still performs fine-ish, 85%. I don't know, whatever.
The scrambling is random?
No, the scrambling is a deterministic function.
Okay.
So every time you have the same scrambling. Okay? It's just to show you that if I change the location of those pixels, the fully connected layer doesn't see it, it's the same. The convolutional neural net instead is going to perform worse. You don't have anymore that advantage with respect to the.
So the scrambling here is that basically with the random permutation, with the fixed random seed. And before we permute, we flatten the image, we permuted the pixels, and then we put it back to the 2D.
Yes?
My question, I think, goes back to the difference between the fully connected and the convolutional neural net in terms of like the training we did. If we would take the fully connected one and just run the training for more epochs, we could still get the same, but with the convolutional one?
No. So if you have the same number of parameters, the modeling power of the convolutional network on natural data is much higher. So given the same number of free parameters for both models, the convolutional neural net can exploit those parameters much more because it doesn't use those extra parameters to try to figure out connection with further away values or with different kernels in every position. So you can reuse your parameters in order to extract in multiple locations the same kind of feature. So convolutional neural net, given the same number of parameters and given that you can deal with data which is, again, have those three kind of main assumptions valid, then it's going to be having a higher modeling power. On the other side, if you have the same modeling power, so convolutional neural net and a fully connected layer, fully connected network, which perform the same with the same accuracy, then you're going to figure out that the convolutional neural net has much less parameters. So given
to add to what Alfredo just said, as you can see from the result, actually the fully connected network had pretty high training accuracy. That's kind of along the lines with what you said. If we train it, we can get very high training accuracy, but the generalization power will be very bad. And on the test set, it's actually pretty low, which means with the same number of trainable parameters, these are less meaningful, as Alfredo said.
So one could devise a strategy where you start with a fully connected network, and then you see which weights they go to 0, or they go really close to 0, and use that as a way to guide your convolutional architecture. No?
Potentially, but then if you just start with many less weights, you're much faster. You have many less computations.
Yeah, but maybe you didn't put enough.
Oh, okay. So every time, okay, sure. This I could have a full course here. initially you're going to be increase your dimensionality of your network, perhaps increasing these 6 here. As soon as you notice, you have to increase it until you see here 100%. So you go and increase your model capacity up to the point where it is 100% able to model your training data. But then it's going to be performing very poorly on the validation set because it's going to be basically memorizing your input data. And that's when you are actually introducing other regularizing techniques, let's say, namely dropout, which is somehow turning off some neurons, or you're even maybe willing to use batch normalization, which is not a regularizing technique, but it works as a regularizer. So again, you should be using all the time batch norm because it performs some kind of regularization as a byproduct, but it's also going to be speeding up your training procedure. So first, you try to overfit your training set. After, when you're sure that you can completely fit your training set, you start adding regularization blocks, which are going to be making you improve performance on the validation set. And when you reach the highest validation accuracy or the lowest validation loss, you stop there. And this is like the cross-validation technique.
So actually about batch norm, it will speed up convergence, but the training itself, time per epoch, won't be sped up. It will speed the
of course, yes.
Speeds up convergence.
Yeah, sure. And it also performs this regularization, which again, I should tell you more why it does. So if someone asks you, let's say in a job interview, is batch normalization a regularization technique? Your answer is going to be no, but it performs regularization as a byproduct. Bless you. All right, any other question? No? Yes?
So, well, you know what is the information that a fully connected network can learn from a picture? Just how many pixels are of one color with respect to...
Right. So if you think about that, can you scroll to the 700 something number? Where is the 700?
You mean...
There's a number. There you go, here.
This one?
So this number here, you can think one image of those numbers is 1 point in a 784 dimension. And then those neural networks are simply moving those points in different regions so that the last layer can just chop them with linear lines, with the hyperplanes. So the only thing, we have seen that yesterday, right? Whenever you have those neural networks, you are warping basically the space. And in this case, you have a 784 dimensional space with those dots. Each dot is representing a specific image. You're just moving things around so that they are all together in different regions, and then you just carve out that region in order to tell, oh, that number belongs to that class. So that's how the fully connected layer works. The other one does something similar, but has a more principled way because it deals with those other properties of the images that we mentioned before. Yes?
Are there ways to use within the framework we have here to sort of you feed it and you just one image and see what it pops to test what you trained at the end, as opposed to just say, okay, cool, I know that it's 94% accurate. Can you sort of simply just give it things and see?
Yes, of course. So that's actually here. If you scroll down to the test loop or wherever the test loop is.
No, test loop. Test loop is here.
Right, so this is testing loop. So you just get your model. You provide here so you get data. You can just write your number on a piece of paper. You just take a picture with your phone.
Yeah.
You resize it to 28 by 28. Then you just you do NumPy image load, something like that, and then you put it here. And this guy is going to be spitting you out the probability. So the probability distribution over the 10 classes is going to tell you how likely that drawing you made is going to be respecting one of the 10 digits. So you can actually do that. Or maybe, okay, next time I'm going to be I can add one extra cell. Okay, I'll do that. Tonight, I add extra cell where you can actually load your image and perform a test. Any other question? If not, thank you for listening, and I see you, I guess, tomorrow for one more lesson on machine learning. Thank you.